Welcome. Today's video we're talking about partial fractions, and so we've already kind of started this discussion and talked about one example, but we're going to go into more depth and you're going to get some practice. So today we're going to talk about how we can decompose rational expressions into partial fractions to help us integrate easier. We're going to do linear factors today, and then we'll do quadratic factors next lesson. So here's a table that kind of helps you know how to decompose these partial fractions. So essentially what we're trying to do is we're trying to get our fractions into something that's going to be easier to integrate. So we're breaking them down into smaller degrees. So when we have improper rational expressions, so the degree of the numerator is larger than the degree of the denominator, go ahead and use long division to set that up so that you get a polynomial times another rational expression, and then you can see if you need to break that rational expression down further. And then the next thing is if we have a factored denominator, then you're going to completely factor the denominator into factors of the form that are linear or quadratic. And so you want to make sure that all of those are irreducible. Okay, so make sure all of your quadratic factors in there are not quadratics that you can factor further. If you have linear factors, what you're going to do is you're going to put a variable on top of each linear factor. If your linear factor repeats, then you're going to have a variable on top of each of those repeating factors, and your variables here are constants. When you have quadratic factors, the numerator that you're solving for is going to be a linear expression where you're looking for, so like bx plus c, it would be what you're looking for. So you're looking for the b and the c, those are going to be your constants. And if you have repeating quadratic factors, you then will go ahead and repeat that factor. So I'll show you how all of this works. We'll see. So distinct linear factors. All right, so here we go. So let's just kind of practice decomposition with a rational expression. So I have 1 over x squared minus 5x plus 6. So the first thing I'm going to do is I'm going to go ahead and factor my denominator. So I see that, sorry, I don't know why I did that. So if I have x squared minus 5x plus 6, I can factor that denominator into x minus 3 times x minus 2. And so then I'm going to write this as a over x minus 3 plus b over x minus 2. If you hear my dogs wrestling in the background, I apologize. And so now what I want is I want this to equal my original fraction. So I want that to equal 1 over x squared minus 5x minus 6, plus 6, excuse me. So if these two expressions are going to be equal, then I can go ahead and multiply both sides by that x squared minus 5x plus 6. And I'm going to get, so x squared minus 5x plus 6, which is the same thing as x minus 3, x minus 2. And when I distribute x minus 3 to x minus 2 over here, the x minus 3's will cancel. And I'm going to get a times x minus 2 plus, and then when I distribute it to my second term here, the x minus 2's will cancel. So then I will get b times x minus 3 equals, and then I just have 1 over here because all of that's going to cancel. And so now I need to solve this expression. And so here's the trick to solve this. So I'm going to keep the 1 over here, and I'm going to go ahead and distribute. So I get ax minus 2a plus bx minus 3b. And if I want to rewrite the left-hand side, I can rewrite that as 0x plus 1. So I'm going to put all my x terms first. So I'm going to have ax plus bx minus 2a minus 3b. So now I can see that a plus b, minus 2a. So a plus b has to be the same thing. My goodness, why can't I write? as 0, right? So I wrote both of these in the term or in the form mx plus b, if you want to think about it like that. So a plus b has to be 0, and my constant term has to be negative 2a minus 3b, which is going to be 1. So now I have a system of equations where I have a plus b equals 0, which means a equals negative b, and I also have negative 2a minus 3b equals 1. So then I can go ahead and substitute in that negative b. So now I get negative 2 times negative b minus 3b equals 1. So I get 2b minus 3b equals 1. So negative b equals 1. So b equals negative 1, which means a would equal a positive 1. Okay? So now if I want to go through and rewrite my fraction, my original fraction, using the decomposition we just found, I would say that 1 over x squared minus 5x plus 6 is going to equal a, so 1 over, and then my first fraction was x minus 3, plus, and then b was negative 1, so I'm going to change that to a minus, and then negative 1 over x minus 2. So that's how we would decompose, and then we would be able to, if this was an integral, we would be able to integrate 1 over x minus 3 and 1 over x minus 2 easier than 1 over x squared minus 5x plus 6. So let's try an example where we have repeated linear factors. Let's see how that affects it, and we're doing integration at the same time. So here we have the numerator is 1 degree less than the denominator. So I'm going to go ahead and factor my denominator. So if I have x cubed plus 2x squared plus x, first thing I'm going to do is factor out an x. So I have x squared plus 2x plus 1. And then I'm going to go ahead and factor that to be x plus 1 times x plus 1. So I have x times x plus 1 quantity squared. So now I'm just going to do my partial fraction part, and then I'll come back to the integration. So if I have 5x squared plus 20x plus 6 over x cubed plus 2x squared plus x, I want to set that equal to, and then here's my thing. So what we do is we put a denominator for each factor, but when I have a repeated factor, so x plus 1 is repeated, I'm going to make sure it's a denominator as many times as it is repeated. But every time I repeat it, I'm going to build up to that degree that it is a factor up. So x plus 1 quantity squared is going to be my denominator. So I have x plus 1 squared. If it was a cubed, I would have a fraction for x plus 1, a fraction for x plus 1 squared, and a fraction for x plus 1 cubed. So whatever the degree is on that factor, you're going to have that many denominators building up to that degree, if that makes sense. So if you have questions on that, let me know. Okay, so now we have this. And so the factors x and x plus 1 are linear. So all of my numerators here are constants. So we're going to have a, b, and c. And so now I'm going to go through and solve this. So I'm going to go ahead and multiply both sides by that x cubed plus 2x squared plus x, which is the same thing as x times x plus 1 squared. So then after I multiply, here it cancels. So 5x squared plus 20x plus 6. And on this side, I'm going to get a times x plus 1 squared plus bx times x plus 1 plus cx. All right, and so now what we're going to do is we're going to do something where we call this like a basic equation. So we're going to let x equal values because we know that no matter what x is, both of these sides have to be the same thing. So I can pick values for x and then make this equation simpler and help me solve for a, b, and c. So the first thing I'm going to do is I'm going to let x equal 0, right? Because I know x can be anything I want. And whatever x is, these two sides have to be the same. So what that's going to do is that's going to eliminate lots of my factors here. So then I'm going to get 6 equals a times 1 plus b times 0 plus c times 0. Right? So I get b times 0 plus c times 0. So now I have a equals 6. So I have one of my variables. Okay? And so then that's going to help me. And so now I'm going to do the same thing for other variables. So I picked 0 because 0 made this factor go away and this factor go away. So now if I pick a different value for x, so I'm going to let x equal -1. And when I let x equal -1, that's going to have this go to 0 and this go to 0. So then I can find the value of c. So if x equals -1, I'm going to get 5 minus 20 plus 6 equals, and then I get a times 0 plus b times 0 minus c. So then I end up with 9 equals c. So now I have c. And then when I plug those in, for, let's say here, let's pick a simple value for x to find b. I'm going to pick 1. We haven't picked 1 yet, and it doesn't make anything 0. So let x equal 1. So if x equals 1, and I have a equals 6, and c equals 9, I can go ahead and plug everything in. So I'm going to get 5 minus 20, plus 20, plus 6 equals a times, and then I'm plugging in 1. So 1 plus 1 squared, plus, and then I have b. Oops, a was 6. I didn't plug that in. 6, and then b we don't know, but then we're plugging in a 1, and then a 1 plus 1 is 2, and then I have 9 times 1. So then I get 31 equals 24 plus 2b plus 9. Solving for b, let's see here, I get -2 equals 2b. So then I'm going to get b equals -1. So then when I put all of this together, we'll do that example next time. So then when I put all of this together, in my integral, I can change my integral from 5x squared plus 20x plus 6 over x times x plus 1 quantity squared dx to the integral of these three fractions. So the first one was a over x, so 6 over x, minus, and it was b over x plus 1, so, oops, plus b over x plus 1, which was -1 over x plus 1, and then plus c, which was 9, over x plus 1 quantity squared dx. And so now integrating this is going to be a lot easier because I know I can use my good old natural log for the first two fractions. So the first one is 6 times 1 over x, so 6 times the natural log of the absolute value of x. And then the antiderivative of 1 over x plus 1, so I have minus, and then the natural log of the absolute value of x plus 1. I don't need to worry about u substitution there because the derivative of x plus 1 is 1. And then my next one, if I think about this as 9 times x plus 1 to the -2, then I'm going to get 9 times x plus 1 to the -1, add 1 exponent, divide by the new exponent, -1, plus c. And then go ahead and simplify that. I'm going to combine these two natural logs together into a single natural log. And that means I have to put that 6 in as an exponent first. So it's subtraction. So it's x to the 6th, and then I subtract. So my denominator is x plus 1. And then plus, and then over here, oops, not plus, it's minus, because I have that -1. So minus, and then 9 over x plus 1 plus c. So that would be our final answer. So go ahead and try the homework, and we will try it with quadratic factors next time.